All right, buckle up, everybody, because today we are going deep, really deep into the world of intelligence.
That's right, we're going to be
I
exploring.
mean, this is the big one, right? We're talking about how did intelligence even evolve in the first place?
Yes.
From like the very first spark of life all the way to us, the human brain.
Yeah.
And, maybe even take a peek into the future with AI. You sent over Max Bennett's A Brief History of Intelligence,
Yep.
and I've got to say, I am ready to unlock its secrets.
It's a fascinating book. I think you're going to get a lot out of it.
Okay, billions of years. That's what we're talking about, right?
That's right.
I mean,
Billion.
billions of years of evolution. That's almost too big to wrap my head around.
It is. It is. It's a huge story.
So I am definitely ready for some aha moments. But where do we even begin with something like this?
Well, I think the best place to start is with the simplest forms of life.
Okay.
We need to go back to what scientists call LUCA, the last universal common ancestor.
Hold on. So you're telling me that the key to human intelligence lies in bacteria?
You got it.
I mean, I'm all for appreciating the little things in life.
Yeah.
But how can bacteria be that insightful?
Well, think of it this way. LECA wasn't just any bacteria, it was the ancestor of all life on Earth.
Oh.
Every single organism, from a tiny little microbe to the biggest whale, shares some fundamental features
Okay.
that were passed down from LUCA.
You're blowing my mind already, I gotta say.
It's pretty amazing when you think about it.
So what exactly did LUCA bequeath to us? Besides existence, of course.
Well, we're talking about DNA, proteins, lipids, carbs, the building blocks of life.
Huh.
You and I, we carry echoes of LUCA inside every cell of our body.
Wow. So even though those ancient organisms, they didn't have brains like ours,
Yep.
they still laid the foundation for everything that came after, right?
They did. They really set the stage.
I'm starting to see the connections here. It's amazing. What happened next in this evolutionary saga?
Well, fast forward a few eons, and we have the rise of cyanobacteria. They might be microscopic, but they were the first true ecosystem engineers.
Okay.
They started pumping oxygen into the atmosphere through photosynthesis.
Wait a minute. Are we talking about the same cyanobacteria that causes those algae blooms in like lakes and stuff that make it kind of gross to swim in?
That's the one.
From bacteria that mess up my swim to the human brain. That's quite a leap.
It might seem strange, but it's true. You have to remember that oxygen was a game changer.
Right.
Before cyanobacteria, Earth's atmosphere was mostly carbon dioxide and nitrogen,
Right.
and their oxygen production set the stage for the evolution of organisms that could use that oxygen to fuel their metabolism, eventually leading to more complex life forms, including those with brains.
Oh, okay. So oxygen equals energy, and energy equals more complexity.
That's it.
Makes sense. But how did we go from oxygen-breathing bacteria to actual brains? What was the driving force behind that transition?
It all boils down to the competition for energy and resources. Life at its core is a constant struggle
Okay.
to acquire and utilize energy in order to survive and reproduce.
Right.
And that struggle was the driving force behind the evolution of intelligence.
So it's like a cosmic game of survival of the fittest, even at the microscopic level.
Exactly. As organisms evolved, they had to find more efficient ways to acquire energy.
Right.
And that's where we see the first brains emerge in a group of creatures called bilaterians.
Bilaterians, isn't that basically just a fancy word for worms?
Pretty much, yeah.
You're telling me that the foundation of my brilliant brain lies in something as simple as a worm?
Well, they weren't just any worms.
Yeah.
They were the ancestors of all animals with bilateral symmetry.
So front and back, left and right we're talking about.
Exactly, meaning they had a distinct front end.
Okay.
And having that front end meant they needed a way to navigate their environment.
Right.
And that's where the first brains came in.
So worms paved the way for, well, brainiacs like us, because they figured out how to steer.
You could say that, yeah.
Amazing.
Those early brains, they weren't about deep thinking or complex problem solving. Their main function,
Okay.
Bennett calls it steering, the ability to move effectively through their surroundings.
Right.
They were like tiny living Roombas bumping around, using simple sensors to avoid obstacles and find what they needed.
Okay, that's kind of a funny thought. I can't believe I'm comparing my brain to a Roomba, but I guess it makes sense.
Yeah.
But how did they know where to go? I mean, were they just randomly bumping around?
Even the simplest organisms have a sense of what's good or bad for them.
Okay.
We call that valence.
Valence, okay.
It's that basic feeling of being drawn toward things that are beneficial,
Right.
like food, and avoiding things that are harmful, like predators.
So even without complex emotions, those early bilaterians had a basic feeling of good and bad.
Yeah, you could think of it that way.
But how did they learn to connect those feelings to specific things in their environment? I mean, were they just born knowing what to seek out and what to avoid?
That's where associative learning comes in. It's the ability to learn from experience.
Okay.
Think of Pavlov's dogs.
Yeah, the bell and the food.
Exactly. They learn to associate the sound of a bell with food.
Right.
Even simple nervous systems can form these associations, connecting specific cues in their environment with positive or negative outcomes.
So even those ancient worms were capable of learning through association.
That's right.
That's incredible.
Yeah.
But hold on. If everything in their environment was happening at once, how did they figure out which cue was actually responsible for, the good or bad thing? Like, wouldn't it be easy to get things mixed up?
That's a great question, and it highlights a challenge that even our brains face today. It's called the credit assignment problem.
The credit assignment problem.
Okay. How do you figure out which of the many things you encounter is actually responsible for a particular outcome? It turns out those early brains were already solving this problem.
Wow.
They evolved mechanisms to prioritize certain cues, like focusing on the strongest stimulus,
Okay.
or paying attention to novelty, and relying on previously learned associations.
Wow. So they were already using strategies that we still rely on today.
It's amazing, isn't it?
It is. But
Right.
how did they evolve beyond those simple associative learning mechanisms?
Well, that's where things get even more interesting.
Oh, boy.
The evolution of intelligence was about to take a major leap forward
Okay.
with the emergence of vertebrates and a whole new way of learning.
Vertebrates. So we're finally moving on from worms.
We are.
Okay, I'm ready for the next level of brain power. Bring it on. But before we do, it's amazing to think that even my ability to learn something new today has its roots in the way those ancient organisms navigated their world billions of years ago.
Yeah, it really puts things in perspective.
It's truly humbling. I can't wait to see where this journey takes us next.
Me too. It's going to be a wild ride.
All right, stay tuned, everyone. We'll be right back after a quick break.
Okay, so last time we left off talking about worms, basically, and how they figured out how to steer.
Yeah, those early steering brains.
Yeah.
It's amazing how far things have come since then.
It is. So what comes next in our grand evolutionary adventure?
Well, we're moving on to vertebrates now. So fish, amphibians, reptiles, birds, and, of course, mammals.
Okay, vertebrates. All right, so we're finally entering, the big leagues of brain power here.
Yeah, we're talking about a whole new level of intelligence.
Okay, I'm ready. What's so special about vertebrate brains?
Well, this is where we see a major breakthrough, reinforcement learning.
Reinforcement learning. That sounds familiar. Is it how we train dogs with treats and stuff?
That's right.
So you're saying our brains evolved to work like that?
In a way, yes. It's all about learning through trial and error, figuring out which actions lead to rewards and which ones lead to punishments.
Oh, okay. So instead of just reacting to, what's right in front of them, like those early worms we talked about.
Yeah, right. Vertebrates could learn from their past experiences and make choices. Like, that would increase their chances of getting something good.
Exactly. They were starting to think ahead.
So it's like they were playing a game and figuring out how to get a high score.
That's a good analogy.
So what was the key to this new learning superpower?
The key lies in a neurotransmitter called dopamine.
Oh, yeah, dopamine. I've heard of that.
Oh.
Isn't that the feel-good chemical?
That's one way to think about it, but it's actually much more nuanced than that.
Okay.
Dopamine is actually a signal for predicting rewards.
Predicting rewards. So it's not just about, the pleasure itself, but the anticipation of pleasure.
You got it. It's about learning what actions are likely to lead to something good in the future.
That's a subtle but important distinction, yeah.
It is. It's what allows us to make choices based on what we think will happen, not just on what's happening right now.
Give me an example. I'm trying to wrap my head around this.
Okay, so imagine you love chocolate.
Who doesn't?
Right. So you see a piece of chocolate, and your brain, based on past experience, predicts a delicious reward. Your dopamine neurons fire in anticipation.
Okay, so I'm already getting excited just thinking about it.
Right. Now, if you eat the chocolate and it's as good as you expected,
Yeah?
your dopamine levels stay elevated.
Okay.
But if you eat it and it's disappointingly bland, your dopamine levels drop.
Oh, so like a letdown.
Exactly. That drop signals a prediction error. Your brain is constantly comparing your expectations with reality and adjusting its predictions accordingly.
So dopamine's like this little accountant in my brain, keeping track of my reward predictions.
You could think of it that way, yeah. It's a feedback system that helps us learn what works and what doesn't.
That's fascinating. Okay, so how does this dopamine prediction system actually change the way we behave?
Well, this dopamine-driven learning system is connected to a part of the brain called the basal ganglia.
Okay, the basal ganglia, what's that?
Think of it as an actor-critic system. It receives those dopamine signals as feedback and uses that information to reinforce successful behaviors,
Okay.
making them more likely to happen again in the future.
So the basal ganglia is like the director in my brain
Yeah.
telling the actors my thoughts and actions, which scenes to replay
Right.
based on how well they were received by the audience, like the dopamine system.
That's a great way to visualize it. And here's the amazing part. This basal ganglia system, with its dopamine connections,
Yeah.
is found in all vertebrates, from fish to humans. It's a fundamental part of how we learn and adapt.
Wow, so it's a really old and powerful piece of evolutionary engineering.
It is. It's essential for survival.
Hmm. And you mentioned earlier that this has implications for artificial intelligence too, right? I mean, does this mean AI is learning in the same way our ancient vertebrate ancestors did?
You got it. This type of learning, it's called temporal difference learning.
Temporal difference learning. Okay.
And it's based on how dopamine functions in the brain. And it's been used to train AI systems to do all sorts of things.
Like what?
Play games, navigate mazes, even drive cars.
Oh, wow. That's incredible. It's like we're taking inspiration from our own evolutionary history to create intelligent machines.
In a way, we are.
That's mind-blowing. But learning isn't just about rewards and punishments, right?
Right.
There's also something to be said for curiosity. Like, how does that fit into this picture?
You're absolutely right. Curiosity is a crucial part of learning. If an animal only sticks to actions that it knows will lead to a reward,
Right.
it might miss out on discovering even better rewards.
Yeah, it's like sticking to the same old restaurant
Exactly.
because you know you'll get a decent meal, but you could be missing out on some incredible culinary experience if you never try anything new.
Exactly. Curiosity drives exploration, it pushes us to try new things, and of course, it's also fueled by the dopamine system. When we encounter something novel, something unexpected, those dopamine neurons fire, triggering a sense of intrigue, that motivation to explore further.
So our brains are wired to be rewarded by novelty and exploration.
That's right.
Huh. I guess that explains why I can spend hours browsing random Wikipedia articles.
Yeah, maybe so.
I mean, it's amazing, but also kind of scary how much our evolutionary history can tell us about our modern-day behaviors.
It is fascinating how these ancient mechanisms still influence us today.
Yeah. Okay, but let's get back to the evolution of intelligence itself.
Right.
What happened after vertebrates? Did the story just stop there?
Not even close. The evolution of intelligence is a never-ending story.
Ooh, okay.
And the next chapter takes us to the rise of mammals.
Mammals, all right.
And a truly remarkable breakthrough, the ability to simulate the world inside their own minds.
Okay, now I'm officially intrigued. Simulating the world inside their heads? That sounds like something straight out of, like, science fiction.
I know, it's pretty mind-blowing.
Yeah. We'll definitely have to dive into that next time.
For sure. It's an important part of the story.
It is. But, before we go, you've already given me so much to think about today.
Yeah.
The idea that our brains are built on, like, these ancient, deeply ingrained mechanisms, it's both humbling and kind of awe-inspiring, you know?
I agree. It really makes you appreciate the complexity and power of the human brain.
Yeah, it does. All right, everyone, stay tuned. We'll be right back to unlock the secrets of simulation after a quick break. Okay, so last time, you were telling us about this incredible idea that mammals developed the ability to simulate the world inside their heads.
Yeah, it's a pretty remarkable ability.
Yeah, I mean, it sounds like something straight out of, The Matrix or something.
Right.
How is that even possible?
Well, it might sound like science fiction, but it's one of the key reasons mammals were able to evolve such complex behaviors.
Yeah.
They developed a new part of the brain, the neocortex.
Okay, the neocortex.
You can think of it like a virtual reality simulator, constantly running scenarios, making predictions about the world.
A virtual reality simulator. So, like, squirrels are running simulations in their heads when they're burying nuts.
Well, maybe not on the level of a high-end VR headset, but the principle is the same.
Okay.
The neocortex allows mammals to go beyond just reacting to the environment.
Right.
They can imagine different possibilities, test out potential actions in their minds, and make decisions based on those imagined outcomes.
That's a huge advantage, right? It's like having a built-in planning department up there.
Exactly. It allows for much more sophisticated behavior.
So how does the simulation actually work? I mean, are we talking about conscious deliberation here?
It's probably not conscious in the way we experience it, but there's evidence that mammals were doing something called vicarious trial and error.
Vicarious trial and error, what's that?
Well, imagine a rat navigating a maze.
Okay.
Before choosing a path, it pauses, looks back and forth.
Right, like it's thinking about it.
Exactly, almost as if it's weighing its options. Scientists believe this shows the rat is mentally simulating different paths, trying to predict which one will lead to the reward.
So it's like a mental dress rehearsal for real-world actions.
That's a great way to put it.
That's amazing. But we were talking earlier about dopamine and reinforcement learning.
Right.
So how does that system fit in with
Right.
this new, simulation ability?
Well, dopamine is still the key player. It's the driving force behind the motivation to seek out rewards.
Right.
But with the neocortex, the brain could actually trigger those dopamine circuits even in the absence of a real physical reward.
Hold on. Are you saying mammals could experience the thrill of reward just by imagining it?
Exactly.
That's kind of mind-bending.
It is, and it allowed them to make choices that weren't just driven by immediate needs, but also by the anticipation of future rewards.
So they could plan, they could strategize, they could make decisions that would benefit them in the long run.
Precisely. It opened up a whole new realm of possibilities.
It's like they were playing 4D chess in their heads or something.
That's a good analogy.
So this ability to simulate, it seems crucial for planning, for decision-making, but were there any other benefits?
Well, it also unlocked a powerful new skill, counterfactual thinking.
Counterfactual thinking. Okay. That sounds very philosophical. What is that exactly?
It's the ability to think about what could have happened
Okay.
if you had done something differently.
Oh, okay.
It's essentially running a simulation of alternative realities in your head.
So like the what-if game.
Oh, right.
What if I'd taken that other job? Or what if I'd bought that lottery ticket?
Right. We all do it. And it's incredibly important for learning by imagining how things could have gone better or worse.
Okay.
You can adjust your behavior in the future, avoid making the same mistakes. It's also closely tied to understanding cause and effect, figuring out which actions lead to which outcomes.
So through this simulation, this ability to simulate, I mean,
Yeah.
mammals gained a deeper understanding, not just of the world around them, but also of their own actions, their own consequences.
Yeah. Precisely. It's a level of cognitive sophistication that really changed the game.
Wow, that's huge. Okay, so where do we go from here?
Well, this sets the stage for the next major breakthrough,
Okay.
the evolution of primates.
Primates. Okay, so we're finally getting to the part where, we become the stars of the show.
Right.
What makes primates so special?
Well, primates developed a unique ability. We call it mentalizing.
Mentalizing. Okay, and what is that exactly?
Mentalizing is the ability to understand the minds of others.
Oh,
It's about attributing mental states, like beliefs, desires, and tensions to other individuals.
so being able to put yourself in someone else's shoes.
Right, and understand their perspective.
It sounds like, that's the basis for empathy, for social connection, all that stuff.
You're exactly right. Mentalizing is considered the foundation for a whole suite of uniquely human social skills.
Like what?
Empathy, cooperation, communication, even deception.
Hmm.
It allowed primates to navigate the complex social world.
Yeah, this makes me think of those nature documentaries.
That's right.
Chimpanzees, forming alliances, competing for dominance.
Exactly.
I mean, they seem so politically savvy.
They are. They have a very sophisticated understanding of the social dynamics within their groups. They can figure out who's in charge, who their allies are, who to avoid.
It's amazing. And all this social intelligence is built on their ability to mentalize, huh?
That's right. It's a crucial ability.
So this mentalizing, this ability, I mean, did it play a role in anything beyond, just navigating the social scene?
It also revolutionized how primates learned. Because they could understand the intentions behind actions, they became masters of imitation learning.
Imitation learning, okay. So they weren't just blindly copying movements. They were figuring out the goal of the action and then, figuring out how to achieve that same goal.
Precisely.
That's a big deal,
Yeah.
right? I mean, that's how we, pass down knowledge. That's how culture spreads.
You got it. It allowed for the accumulation and transmission of knowledge and skills across generations.
Wow. So we've come a long way from those simple worm brains
Yeah.
to the complex social intelligence of primates. It's incredible. But there's still one piece missing, right? Language.
Ah, yes. Language.
Yeah.
The crown jewel of human intelligence.
How did that evolve?
Well, While there's still much we don't know about its origins, it likely emerged from those same social and cognitive foundations that gave rise to mentalizing.
So our ability to understand other minds
Right.
was kind of like a prerequisite for developing language.
Exactly. You need to be able to grasp the idea that other people have thoughts and beliefs that may be different from your own.
Right, right. And did language, I mean, did it evolve kind of like gradually?
Most likely. Starting with simple gestures, vocalizations that conveyed basic emotional states.
Oh.
Much like how babies communicate before they learn words.
Right, like when a baby cries to signal that they're hungry.
Exactly. And as primates became more skilled at mentalizing, their communication became more complex, eventually leading to the symbolic language we use today.
And don't forget about simulation too, right?
Yeah.
I mean, I'm guessing that also played a role.
Absolutely. Our ancestors' ability to simulate, to imagine things that weren't physically present, was crucial for developing those abstract concepts.
That's amazing. So from simple bacteria to creatures capable of, building rockets and writing poetry,
It's quite a journey.
all thanks to this incredible chain of evolutionary breakthroughs.
It really makes you appreciate the power of evolution.
It does. I mean, what an amazing story.
It is, and the most fascinating part is that the story doesn't end here.
So we're still evolving, even now.
That's right. The
Yes.
evolution of intelligence is an ongoing process.
Wow. And with the rise of AI, who knows what the future holds?
That's the big question, isn't it? But understanding the history of intelligence can give us valuable insights into the possibilities and challenges that lie ahead.
This has been an incredible deep dive. I mean, it's really made me realize how interconnected all these different aspects of intelligence are, and how much our own brains are a product of this, this long, fascinating evolutionary journey.
It's a humbling thought.
It is, it is. Well, that's all the time we have for today. I want to thank you so much for joining us on this epic exploration of intelligence.
It's been my pleasure.
And to all our listeners out there, we hope you've enjoyed the journey as much as we have.
And that you've learned a thing or two along the way.
Absolutely. Until next time, keep those brains buzzing.